All right, so we are on page 20 and we're looking at effect size. So let's remember from chapter 8, effect size again is a measure of practical significance. So while statistical significance p-value tells us whether or not there is evidence of a difference in our population, the effect size tells us how large that difference may be. So you will hear this referred to as the magnitude of the difference typically. The most commonly used measure of effect size when studying the mean of one group or the difference between groups is known as here it is, Cohen's d. So again, the most commonly used measure of effect size when we're studying the mean of one group or the difference between two groups, that is called the Cohen's d. It is a very simple measure in principle, but it has quite a few wrinkles once you start digging into the details. So Jacob Cohen himself defined it primarily in the context of an independent means t-test, specifically the student t-test. And in that context, a natural way of defining the effect size is to divide the difference between the means by an estimate of the standard deviation. So Cohen's little d is mean 1 minus mean 2 divided by standard deviation. As we can see, the equation is also referenced on page 20. So Jacob Cohen suggested a rough guide for interpreting the Cohen's d, or the little d, and we can see that on page 20 in table 9.1. So here's a very rough guide to interpreting Cohen's d. So if your Cohen's d is about 0.2, the rough interpretation is that there is a very small effect. If your Cohen's d is about 0.5, the rough interpretation of your Cohen's d is that there is a moderate effect. If your Cohen's d value is 0.8, the rough interpretation is that there is a large effect. All right, so let's dig a little bit deeper into this. So you might think that interpreting Cohen's d would be pretty unambiguous, but it's actually not. This is largely because Cohen wasn't too specific on what he thought should be used as the measure of the standard deviation. So in his defense, he was trying to make a broader point in his book and not to nitpick the tiny details. As discussed by McGrath and Meyer back in 2006, there are actually several different versions that are in common usage, and each author tends to adopt a slightly different notation. So for the sake of simplicity, as opposed to accuracy, we're going to use the little d to refer to any statistic that you calculate from the sample, and the Greek letter delta to refer to as a theoretical population effect. So unfortunately, that does not mean that there are several different things and they're all called d. So most people would say that the only time that you would want the Cohen's d is when you're running a one sample mean z-test, a one sample mean t-test, an independent means t-test, or a paired means t-test. And our software that we're using, the JASP software, it does have an option to calculate the effect size for all of these tests. So let's look at which of these is actually, is actually being computed. And that's what we're going to get into next. So we're going to first look at the Cohen's d for the stuff that we looked at yesterday, which was the one sample mean z-test and the one sample mean t-test. So the simplest situation, again, to consider is the one corresponding to a one sample test. So in this case, again, this is the one sample mean and the one hypothesized population mean. So if you're conducting a one sample mean z-test, then you must have the population standard deviation. And then the Cohen's d would be computed as the equation at the bottom of page 20. If you're conducting a one sample mean t-test, we also have another equation at the bottom of page 20 for reference. And then we'll just use our usual estimate of standard deviation. So again, therefore, we end up with these equations, and they look like exactly what we have been studying to do the longhand math. We're going to move to page 21, and we're going to go back to our Dr. Zeppo example. So we're going to use the Dr. Zeppo data set that we first used when we were doing the z-tests and t-tests, and as we recall, in that example, the sample mean was 72.3 points, and it had a standard deviation of 9.5 points. The hypothesized population mean was 70 points. And so in order to compute by hand the Cohen's d for this test, we're going to use the equation and do our input as follows. So Cohen's d, little d, equals 72.3 minus 70 divided by 9.5, and we get the value of 0.242. This means that the students in Dr. Zeppo's class are achieving grades with the mean equal to 72.3 and about a 0.242 standard deviation higher than the hypothesized population mean of 70 points. So judged against Cohen's rough guide, this would be a small effect size, as we just talked about. So if we were to write this data up in proper format, it is definitely common for us to need to report Cohen's d with our t-test statistics. So here's an example of how to report these results. So with a sample mean of 72.3 points, standard deviation equal 9.5, there is not sufficient evidence to conclude that the population mean is different from 70 points. T19 equals 1.08, P equals 0.293, D equals 0.24, 95% confidence interval, 67.8, 76.8. Note that when we're reporting our Cohen's d, a 0 is included before the decimal place. It is little d equals 0.24 if the value is less than 1. So again, it is not reported as little d equals 0.24. It's reported as little d equals 0.24. This is because it is possible for Cohen's d to be greater than 1. So now we're going to look at Cohen's d for our students' t-test. So the majority of discussions of Cohen's d, they focus on a situation that is analogous to the students' independent samples test, the students' independent samples t-test. And it is in this context that the story gets a little bit messy. So in this scenario, there are going to be several different versions of Cohen's d that you might want to use. So to understand why there are multiple versions of the Cohen's d, it will help to take the time to write down or examine this formula on page 21. It's in section 9.6.2. So again, to understand why there are multiple versions of the Cohen's d, it helps to take this time to either reference or write down this formula, which corresponds to the true population effect size, which is denoted now as delta. So it is pretty straightforward. So delta equals mu1 minus mu2 divided by standard deviation, where mu1 and mu2 are the population means that correspond to your group 1 and group 2 respectively. And your standard deviation is your standard deviation being the same for both of your populations. So again, the obvious way that we would estimate our delta is to do exactly the same thing that we did in the t-test itself. For example, to use the sample means as the top line and the pooled standard deviation for the bottom. So in this particular second equation of 9.6.2, in the denominator, we have the estimated standard deviation with the subscript little p. So with this estimated standard deviation subscript p in our denominator, this is the exact same pooled standard deviation measure that appears in the student t-test. This is the most commonly used version of Cohen's d when applied to the outcome of a student t-test, and it is the one provided in our software. It is sometimes also referred to as the Hedges G statistic. However, there are other possibilities which we will briefly describe. Firstly, you may have reason to want to use only one of the two groups as the basis for calculating the standard deviation. This approach, often called Glass's delta, it only makes the most sense when you actually have good reason to treat one of the two groups as a purer reflection of the natural variation than the other. This can happen if, for instance, one of the two groups is a control group. Secondly, recall that in the usual calculation of our pooled standard deviation, we divide by n-2 to correct for this bias in the sample variance. So in one version of Cohen's d, this correction is omitted, and instead we just divide by big N. Now, this version makes sense primarily when you're trying to calculate the effect size in the sample rather than estimating an effect size in the population. And finally, there is a version based on Hedges who pointed out there is a small bias in the usual pooled estimation for Cohen's d. Thus, they introduce a small correction by multiplying the usual value of little d, Cohen's d, by n-3 divided by n-2.25. In any case, ignoring all those variations that you could use, that you could make use of if you wanted. So, hold on, let me say that again. In any case, ignoring all those variations that you could make use of if you wanted, let's now have a look at the default version that is going to be used in our statistical software that we're using. So in JASP, and we're going to go back to the example that we looked at with Dr. Harpo's class, where we compared the scores of the students that were assigned to the two different tutors, Anastasia and Bernadette, and that was way back in section 9.3.2. So We're going to go back to our statistical software to rerun this analysis, but this time when we go under the additional statistics heading, we're going to check the box next to effect size. And by default, the effect size used in our statistical software will compute for an independent means t-test using, by default, the effect size that JASP will compute for this independent means t-test is Cohen's d. Now this output will be something that we're going to double check, and it's in the figure on page 22, and it's figure 9.15. So again, in this figure, we have Cohen's d, and it's equaling 0.74. Let's double check. Yep, that looks right. And this indicates that the grade scores for the students in Anastasia's class are on average 0.74 standard deviations higher than the grade scores for the students in Bernadette's class. So using Cohen's standards from table 9.1 and using what we know about the test grades, we would say that this is a large effect size. And in the JASP statistical software, when we check the box to add the Welch test to our output, a slightly different value of the Cohen's d then appears, and it is adjusted down to the Cohen's d equals 0.724. And here, the JASP software is adjusting Cohen's d to use a measure of the standard deviation that would be consistent with the formulas that we saw earlier for the Welch's t-test. And now we're going to move into section 9.6.3, and we're going to look at the Cohen's d for the paired samples t-test. So finally, what should we do for the paired samples t-test? So in this case, the answer will depend on what it is that you're trying to do. So this software, the JASP statistical software, assumes that you want to measure your effect sizes relative to the distribution of your different scores, and the measures of the little d that you will calculate is this equation on page 22. So the Cohen's d, or the little d, equals the big D, the mean of the big D divided by the estimated standard deviations subscript big D. Again, where the denominator is the estimated standard deviation with the subscript big D, and this is the estimate of the standard deviation of your differences. So going back to our example, we're going to look at Dr. Chico's class, which is section 9.5.1, and we have rerun this analysis in JASP. We requested effect size. These results are shown in figure 9.16, and from this, we can see that Cohen's d equals 1.45, indicating that the students' scores on the second test are on average 1.45 standard deviations higher than the scores on the first test. Using Cohen's standards, this is a huge effect. However, I can also see that the mean difference was 1.41 points, which from the context I would say is a very small difference. Like for a student, it would have low practical significance. This is actually one example of why it is important to understand the context and the data, particularly when it comes to interpreting your effect size, which tends to be subjective compared to other areas of statistics. This is the version of Cohen's d that gets reported by the JASP paired samples t-test analysis. The only wrinkle is figuring out whether this is the measure that you want or not. So to the extent that you care about the practical consequences of your research, you often want to measure the effect size relative to the original variables, not the different scores. So for example, the 1.405 point improvement in the Dr. Chico's class data over time, it's very small when you measure it against the amount of between student variation that is within the grades. So in which case you would use the same versions of the Cohen's D that you would use for a student or a Welch t-test. It's not so straightforward to do this in our JASP software, and essentially you have to change the structure of the data in the spreadsheet view, but we're not going to worry about that right now. So in summary, effect size, again, it's a crucial measure that complements statistical significance by quantifying the magnitude of the difference between your groups or your conditions. And the Cohen's D is one of the most commonly used measures of effect size within psychological research, providing a standardized way to interpret the practical significance of your findings. So by understanding and reporting effect sizes, researchers can actually offer more meaningful insights into their data beyond the binary outcome of hypothesis testing. So for example, reject or fail to reject the null hypothesis and only looking at statistical significance. So let's take a look here. So we're going to pause here. We're on page 23 of 33, and our next review will have us looking into the plotting the let's see. I see it right here. So the next section, we're going to look at histograms and QQ plots and the Shapiro-Wilk test. And then after we look at those, we're going to get into non-parametric alternatives, and we're going to look at the Wilcoxon signed rank test and the Mann-Whitney U test. But for now, that is enough.